Welcome back to Tutorial 4. In the last coding activity, you took data from a diverse set of CMIP6 Earth system models and showed their projections differed from one another. And in this tutorial, we're going to be talking about how we can use those differences to quantify our uncertainty in CMIP6 projection. So we've already talked about some of the reasons why each CMIP6 model produces a climate that's distinct from Earth's own climate and from the climate predicted by other CMIP6 models. Particularly in the last tutorial, we talked about the different ingredients that go into a model and how there are human and scientist choices made when choosing which ingredients to put in, whether it's different parameterizations or physics, or using different choices for the numerics and discretization of a model. But there's also a physical source of differences between each model's simulations, which is called internal climate variability. Especially what this represents is the complexity and the chaos of the Earth system. So the Earth system is governed by highly nonlinear and complex equations. And those equations mean that if you make a small perturbation in one place at a specific time, it can lead to a much bigger perturbation in other places at a later time. And that internal climate variability is analogous to the butterfly effect that you've probably heard of. If we only had one Earth system model projection, and we were looking at that projection, then we wouldn't know how much these different factors contribute to our uncertainty in that projection. Is there a lot of uncertainty due to the choices that we made when building that model? Or is there a lot of uncertainty in that projection due to the internal climate variability with that model? Fortunately, if we have an ensemble, specifically a multi-model ensemble like CMIP6 produces, then we can compare those different Earth system model projections to estimate our uncertainty in the future climate projections they produce. And this uncertainty incorporates both that physical uncertainty and the human-driven choices made building the models. This figure on the left shows an example of some of the 30 or so models that I used to create a specific figure for the recent IPCC report. If you look carefully, you might see some of the models that you've already been using today listed on here. And when we have a group of models, these multi-model ensembles, then we can look at how those model projections differ amongst the group of models. And so that's what this figure shows as an example from the IPCC report of the global mean temperature projections going out to almost 2100. The two different colors here represent two different scenarios. Let's just look at the blue SSP1 2.6 scenario right now. What you can see is that there are a diverse range of projections coming from different models. So each of those individual lines is a different CMIP6 Earth system model and its projection. Another thing that you might notice is that these projections in 2090, the end of this time series, don't follow a Gaussian or normal distribution. Specifically, what a Gaussian or normal distribution describes is a distribution that is peaked at a specific mean value and then decays symmetrically to either side. But if you look at those blue projections in 2090, then you can see that there isn't a clear grouping of projections around a mean value with a decaying number of projections on either side of that mean. What you instead see is that there are a pretty evenly spread range of projections from those models. And for this reason, we don't use standard deviations, which are a typical metric of normal or Gaussian distributions, to quantify model uncertainty. Instead, we use quantiles, which are a way of saying what percentage of models lie within a certain range for their projections. And specifically, the IPCC, as you encountered in the invited speaker talk today, has some specific language that it uses to communicate this uncertainty to a diverse audience. Specifically, the things that they often talk about are likely ranges, which in the context of CMIP6 refers to the range of projections within the middle 66% of model projections, and a very likely range, which encompasses the middle 90% of model projections, so it ignores the bottom and the top 5% of model projections. And this is an easy way of analyzing and quantifying the uncertainty of projections, which is what you'll do in this next tutorial. But as a quick aside, I also want to point out that there are other metrics for quantifying uncertainty amongst model projections. For example, when you work with maps, you might have specific regions where the changes have different signs. And so you can look at a specific region and define something like high model agreement, which would tell you that 80% or more of the models project the change in a specific region will have a certain sign. So there will be an increase in temperature in a specific region, and therefore less than 20% of models predict a decrease in that region.